here all these reasons and the drivers for this decline, but pesticides and intensive agriculture covering this part here, you see that this is a considerable part of the cake of the driver. So they are toxic and they damage our environment. Second reason is they are used in extremely high amounts almost everywhere in the world. And looking at these numbers here in tons used worldwide, you see that this is ever increasing. So these are the reasons why I start with pesticides. Later on, I will also talk about other chemicals briefly. So the first gap that I see is fate studies, that means degradation studies, and effect studies, that means ecotoxicology of pesticides, are investigated with single substances. But in the agricultural reality, pesticides are always present in mixtures. Pesticide mixtures result from first combining different products for an application. So the farmer, depending on the infection pressure, mixes 2, 3, 4 products in so-called tank mixtures. Second, farmers not only once go to the field and apply these tank mixtures, but they do it several times. So subsequent applications during the growing season of a crop, which we call spray series. And thirdly, residues accumulate over residues over the years. So you always, in agricultural fields, have mixtures of pesticides. So we analyzed almost 900 spray series in part of Europe, 5,000 applications, 539 pesticide products, including 225 active ingredients for 12 crops. And you see here the 12 crops, the main crops used in Europe, but also probably in China. And here is the number of applications of these tank mixtures. At each spray event, at least one active ingredient, most often 2 or more, either as regulated mixture or as individually prepared tank mixture is applied. And you see in all cases, it's not only one application, but more than one application. And the top is the orchids, for instance, apples. You see that 20 applications are occurring in one agricultural season. This is an example of an apple orchid treatment. And you see here between April and September of a year, all these products are applied. I increased the figures here so that you can see which products have been applied. And this mixture makes a difference. Both the effects and the fate of pesticides differ in mixtures compared to single substances. First, coming to the effects. So here you see the ETR, which means the exposure toxicity ratio, which is the sum of the predicted environmental concentrations of all these products in the apple tank mixture spray series that I showed in the last slide, divided by the no observed effect concentration. And you see that these two pesticides, thiacloprid and flucriconazole, are the most toxic ones. And in our calculation, the degradation of these applications is considered. So here is the application of, let's say, one pesticide. We'll take this one here, the thiacloprid, one application, and then it is degraded over time. And flucriconazole, for instance, is applied here but it does not degrade in a reasonable time. You see the half-life is longer than 700 days in agricultural soil. And the mixture of all pesticides of this spray series that I showed here is shown in the top. So this one is the mixture effect. And of course, the pesticides are degraded, or part of them are degraded, and then you come to this diagram. If you take the reciprocal value, the toxicity exposure ratio, which is 1/ETR, then you can demonstrate that organisms are at risk. This blue line here is the toxicity exposure ratio limit defined by the European Commission for earthworms, taking into account the no observed effect concentration von Eisenia fetida, a compost worm, and we considered the concentration addition mode for these, and you see that this trigger value is surpassed in this mixture after about 120 days. So the organisms are at risk, and the recovery within the year is not given. So this mixture leads to toxic concentration, to risk of these organisms. Yes, we have published this 2 years ago. And it's not only the effects, it's also the fate of pesticides that differs in mixtures compared to single substances. So we did 2 studies with 2 PhD students, one in soil working, one PhD student working with soil, the other with water sediment systems. And we investigated the effects of fungicides on the fungal biomass. And our hypothesis is that other components of a pesticide mixture are degraded differently compared to when this pesticide is tested alone. To make it a little bit easier, understandable, so we tested the degradation of the herbicide iodosulfuron methyl sodium, which was radio-labeled, and it was added at the recommended dose. It has a half-life between 1 and 22 days. And we tested the degradation either of this herbicide alone or in presence of these 2 fungicides, tebuconazole and prothioconazole. These 3 components are a mixture that is sold by the companies. So farmers use these mixture for agricultural applications. So it's not an artificial combination of pesticides, it's a commercially available mixture. And what we see here in these diagrams, so in the y-axis is the percentage of applied parent compound, which is the herbicide, the radio-labeled herbicide, and the x-axis is the incubation time. It's difficult to read, therefore I increased it here. And you see here on the left side the disappearance of the parent compound, and on the right side the formation of the first major metabolite. And you see the herbicide alone is degraded, reflected by the green line, and the herbicide is degraded in presence of the fungicides much slower than the herbicide in 3 different soils, as you see here. And the same occurs for the formation of the main degradation product. It's faster formed when the herbicide alone is tested, and it's slower formed when the fungicides are present. So if industry investigates the degradation of a herbicide for authorization, this DT50 is not reflected in the agricultural reality because there are always fungicides present, or very often fungicides present, I must say. Yes, we have published this also, by the way, in your journal EEH. And now I come to a small excursion, let's say, to the non-extractable residues, but very short. If you have a pesticide or any other xenobiotic and it enters the environment, after some time, extractable residues are formed that you can analyze that you can extract and analyze by HPLC, mass spectrometry, or gas chromatography, or whatever. Also, mineralized products like carbon dioxide and other volatile residues are formed. And you always observe that a certain amount of the xenobiotic is remaining in the soil, which we call non-extractable residues. And there is a decades-old debate whether these non-extractable residues are considered a safe sink or a hazard. And we did a lot of studies regarding non-extractable residues because so far, before we did this investigations, you can only quantify the amount of NER by using radio-labeled or stable isotope labeled compounds. So you can only quantify, but not identify what these residues mean. And one method to investigate is cellulation. So by this method, exchangeable protons or functional groups like carboxylic groups, OH groups, and H2 groups are replaced by organic residues of the cellulation reagent. This means that hydrogen bondings are cleaved and are not able, the molecules are not able to form hydrogen bridges. If you consider this an aggregate of humic acids, fulvic acids, and so on, these black dots here, with some pesticide, the red dots inside. If you cellulate these aggregate, it will break down in smaller units because of the missing hydrogen bridges. And then you have two cases. Either the residues are released, and we interpret this that the residues have been just bound in the holes of the humic material, so they were only sequestered, and we call these residues type 1 NER, but they are so strongly bound by this binding to the holes that they are not extracted by usual organic solvents. Only by the cellulation they are released. And the other possibility is that these residues are still sticking to these released humic acid and fulvic acid molecules. You can differentiate both parts by size exclusion chromatography. If you see that these residues are free, you can distinguish this from the residues which are still bound to large molecules here. We call these residues type 2 NER. There is also a third type of NER, which the group of Matthias Kästner developed, and we continued his work by using also radio-labeled compounds to investigate this kind of residues. For instance, you have this pesticide here, radio-labeled. It is degraded by microorganisms to small molecules which are used by the microorganisms to build up biomass. And biomass, for instance, amino acids, but also nucleic acids, phospholipids, and other compounds. And these amino acids, they carry the radioactive label. And by using two-dimensional thin layer chromatography, you see that here amino acids are formed, and we identified these amino acids like leucine, isoleucine, leucine, phenylalanine, valine, proline, threonine, serine, and so on. We analyzed these residues by GCMS, or LCMS. So this is the third type of NER. 3 types, 1 sequestered, 2 covalently bound, and 3 type 3. And this has also been published, of course. Yes, so that's what I just said. We have the 3 types: slow release, stable binding, and natural compounds like the amino acids. And it is important to know that all chemicals form such NER in varying amounts. So these sequestered residues are slowly released from a humic matter under natural conditions. And therefore, our European Chemicals Agency considers this type of NER for the persistence assessment. If you can demonstrate that in these residues, the parent compound or important metabolites are formed, then they have to be added to the persistence, considered in the persistence assessment. And you see here that this is the European Chemicals Agency, that these NER type 1 type, they have to be considered for the persistence. Contain the parent compound, transformation products, or both. Okay. The other types are not environmentally relevant because they are strongly bound, are not released under natural conditions, and these type 3 are into biomass, so they are natural compounds and are of no concern. So coming back to my topic, the mixtures, you see that measuring the non-extractable residues of the herbicide alone, you have 54% of the applied radioactivity being NER. And in the presence of the fungicides, you have significantly lower amounts of NER. So more is extractable. So more of these residues are extractable. And also the percentage of the type 1 and type 2 NER is different. So the conclusion is that this mixture makes also regarding NER a difference. Gap 2, a further gap. Impact of further stress is not considered in fate and effect studies. And by further stress, I mean drought, increased temperature, eutrophication, or soil compaction. If you see here on this axis, the so-called, or what we call the system state of an ecosystem. So that could be for a soil, for instance, the enzymatic activity, the degradation potential, the community of mites or colembula, or the enzyme activities, and so on. And we have here soil not contaminated, the black line. Under certain conditions, this system has a certain system state, let's say enzymatic activity. If a further stress occurs, the system state is changed, let's say, seen by this arrow here. But if the stress is not high enough, the bowl will return to the original state. But if the stress is high to surpass the resilience of the system, which is this arrow here, the system state will come to a different position afterwards. In the contaminated soil, which is the blue line here, we have in principle the same situation. It has a certain system state, and if a stress occurs, low stress, then it's the same as with the uncontaminated soil. But if the stress is high enough, the resilience of this contaminated soil, which is lower than the resilience of the uncontaminated soil, will easier fall into another belly, so into another system state. In soil, we have always a multitude of further stress factors. So you see all these surface crusting, temperature, of course, diseases, waterlogging, and so on. I will only talk about pesticides. Well, I did this already. I will also show some example, one example on drought and on compaction. For instance, compaction. If you compare agricultural machinery, let's say 20 years ago or 30 years ago, 1 ton, for instance, or 1,000 kilograms, nowadays agricultural machinery is much heavier. Here you see the composition of solids, water, and air of an ideal, so-called ideal soil. And if this soil is compacted by such heavy machinery, the difference, the combination of these three components, important components, which trigger, of course, also the biological activity of the soil, is different and impacted. So compaction will impede water and air transport in the soil. It will reduce microbial activity, and it will also have an effect on growth of crops. Regarding drought, you see here the microbial biomass on the y-axis, and you see the water content going from wet soil to very dry soil. And the microbial biomass follows a certain pattern, and you see here that under drought conditions, under prolonged drought conditions, the microbial biomass becomes very, very low. And this means that pesticides will be degraded more slowly under drought. These effects are not considered in any degradation studies of new pesticides, and it has to be changed, I think. There are further gaps, which I will not mention today because it's going too much into other fields. Important organism species are not tested, like wild pollinators, amphibians. More consideration of indirect effects is needed. Drift reducing and habitat measures are often missing, like hedges or vegetated strips. And I think, or many people think, that the environmental awareness of many farmers needs to be increased. So they have to be better educated regarding the fate and the effects of pesticides. Okay, so that was the part on pesticides. Now I turn to a more general approach on other chemicals. I talked about pesticides, but as you all know, many other chemicals are on the market. And a recent publication by Zhanyun Wang, he found out that it is not the 100,000 that is always mentioned in such lectures, but that it is more than 350,000 different chemicals and products on the market. And of course, not only the pesticide, the chemicals, but also their transformation products of all these chemicals are around. Production of chemicals is ever increasing. You see here in this publication by Person et al. That for most pesticides cited here, including, of course, pesticides themselves, but others as well, production is increasing. And in the UNEP program, in the UNEP report on Global Chemicals Outlook 2, it is, I saw the sentence that the chemical industry economy may double by 2030. So this trend is going on. So Zhanyun Wang and other authors, also I was a co-author of this publication, we asked for establishing a new panel on chemicals and waste. An intergovernmental panel on chemical and waste, like that on climate change, IPCC, and biodiversity loss, IPBES, would have several advantages. It could help to speed up the regulatory action on banning dangerous substances by better exchange with politicians. Long years ago, I wrote a paper on the time that is needed after first indications that a certain sort of chemicals is toxic or does harm to the environment. That the time from this event up to regulatory actions, banning substances, is very long. Extreme example is asbestos, where almost more than 100 years ago, it was found that people exposed to asbestos, like the chimney workers, have developed cancer and so on. And it took almost 1 century until this asbestos has been forbidden. And there are other examples like tributyltin or this fuel ingredient, methyl tertiabutyl ether, and engineered nanoparticles, which have not been forbidden until now, and others. So the time is much, much too long, and this panel could help to speed up. It would manage missing chemicals, because of all these 350,000 chemicals and products, only a small part has been investigated. By increasing the scientific network and broader engagement of natural, social, legal, and economy scientists. And it could improve the horizon scanning for new or emerging contaminants. In March 2022, there was the United Nations Environment Assembly in Nairobi, and the resolution to establish such a panel was adopted. So our science paper was quite successful, I think. And I read in the European Commission press release of February 2022 that beside other activities, also creating a science policy panel for chemicals, waste, and pollution, which will provide similar support in dealing with these problems as the IPCC, IPBES, or IRP provide prospectively to climate, biodiversity, and natural resource policies. So we are quite confident that by the end of 2024, such a panel could be established. So my last slide, the conclusion. Predicted pesticide concentrations are often not in line with measured real concentration. And one reason for this is this mixture effect. Conventional intensive agriculture and pesticide use contributes to global biodiversity loss. The risk assessment of pesticides should be updated. Mixtures of pesticides are the rule. Tank mixtures, spray series, accumulation over years. Fate and effects of pesticide mixtures differ compared to individual substances. Further natural and anthropogenic stress factors complicate processes. And finally, we need a global science policy body on chemicals and waste, like IPCC and IPBES. And with this, I'm finished, and I thank you for your attention.
Thank you, Andreas, for this very interesting talk. So, Dr. Andreas Schäfer introduced us the gaps in the pesticides research, so the two gaps, and then also another new panel to be established for international, in the international organization, IUPAC, so the IPCW panel, to dealing with the other chemicals. So now it's open for discussion and questions. Is there any questions? So maybe I start the question. So Andreas,
yeah,
you showed us the NERs, the non-extractable residues, the formation of the non-extractable residue, especially the type 1, is sequestration in chemical substances humic acids and fulvic acids.
Yes.
So, and I think it could be also possible that this type 1 NERs are also sequestrated in the pores of inorganic matrices.
Absolutely.
Yeah?
Yes, I'm sure that happens also. Yes.
And do you have an idea how to separate this type 1? So they are included, for example, in the clay pores, clay mineral pores.
Yes. But if I would be a young PhD student now, and my professor would ask me this question, then I would probably buy different clays that you know, and first test whether abiotically some residues of these pesticides are trapped by these clay particles. But of course, this is only abiotic. And then, maybe I would use maybe a simplified soil mixture, so of microbially active parts and clay, make an incubation and extract the humic matter afterward, or maybe it's difficult. Extract the humic matter as good as possible, and test only the remaining inorganic fractions. But of course, you know that this is not so easy to really separate this. Yeah, it's a tricky question. Of course, you are right. It's not only the organic matter of soil that keeps such sequestered residues, but for sure also the inorganic part. Yeah.
And this simulation would not work for this type 1 inorganic matrix.
It would not work. Yes, I think yes. Why should it work? Because there is no. I don't think. Yeah, but yeah, it would be maybe possible. Maybe also, what I would do then, maybe as a second step, I would first use the pesticide and degrade it in simple microbial consortia, and extract these residues and incubate these with the clay particles alone, and see whether that makes a difference. To consider also the microbial breakdown of the pesticide. But of course, it's tricky. But probably I would do these two experiments in the beginning.
Yeah. Okay.
Unfortunately, I'm not young anymore.
Yeah, maybe we should try it in Nanjing University. You are adjunct professor at our university. You can supervise students to do it.
Yeah, we can ask students of your group to do such experiments. Yeah, why not? Yeah, I'm happy to do this together with you.
Okay, good. And more questions? Here is one from Yang Xiaomei. As you mentioned, predict pesticides concentration differs from mirrored concentrations. How would you suggest to validate or correct this? Which factors you would add in the model?
To predict the real concentrations is very tricky, because as you all know, it depends on not only on the type of chemical that is investigated, what functional groups it has and how reactive it is, but also on the environmental conditions, on the soil type, on the humidity of the soil, the temperature maybe also, and so on. I think prediction is difficult. Monitoring is important. Soil monitoring is an important issue. In Germany, for instance, we have a strong monitoring program for residues in waters, in streams and lakes and so on. But we have none for regular monitoring of soils, not only on the agricultural fields, but also beside the agricultural fields, because this is important. I mean, one can consider the agricultural field as a factory making crops, and as long as it works, one might say, okay, there's low biodiversity, but anyway, we can grow wheat or corn or whatever. But the areas outside of the agricultural fields, they have to be protected. And the regular monitoring of pesticide residues in soil should be installed in all countries where agriculture plays a big role. But prediction of these things is very, very difficult, I think.
Okay.
So we had a big project 2-3 years ago on developing a concept for soil monitoring in Germany. And we also estimated the costs related to such monitoring studies in soil. It's big costs, but compared to other costs like supporting military and supporting human health and so on, it's comparable. It's not impossible to have such monitoring program. So my answer is increase the monitoring strategies in your country, in all countries, and modeling is fine, but to really predict what you see. I mean, I had several slides that I could also have shown. There are so many papers showing that all these residues of pesticides, which have classified as easily degradable, they are saved in the soil. They are staying there for years or centuries even. And you can extract these residues 10 years after the application still. So to predict this is very difficult. Monitoring is the answer.
Yeah, Yang Xiao may respond to your answer. He or she said, indeed, we are working on Lucas project in Wageningen University. Yeah, you can read this here.
Indeed,
and try to.
Yeah. Yes, I heard about this. What is the name of the project? I heard about this in Wageningen, and we are facing such problems, and students are struggling. Yeah, I know. But I heard also that they found already incredible high residues of pesticides also in dust in the atmosphere, in the atmosphere that we breathe. Very high concentrations on vegetation and in organisms and in soil, of course. Yeah, very good that Wageningen is working on this.
Okay. Thank you for Dr. Yang.
Yeah,
other question?
Yeah, very good that your student did this. Very good.
Yeah. Other question? Yeah, I would like to ask you another question.
Yeah.
So also about the effects of the mixed compound. So you observed in the presence of fungicide, the degradation of herbicide decrease.
Yeah.
So this is also a negative effects from another coexisting chemicals, although sometimes there is also positive effect, for example, stimulate the degradation of one compound by another compound.
I have no clue on this. We have never found this, but I will not exclude it. It is possible. Yeah, maybe. I don't know. I have not observed this. In our studies, we did not go, and there are only few papers on this effect, and I don't remember any of these papers saying that you have faster degradation in presence of a certain fungicide. I did not see this. Yeah, but could also be, yeah.
So you mean always the mixture of herbicide with fungicide, or sometimes also two herbicide or the two fungicide together?
Mm-hmm.
So in this case, maybe one herbicide can stimulate another herbicide degradation.
Well, if they are structurally similar and the microorganisms are adapting to the stress, then you may also see a faster degradation. Yeah, that could be. If you, let's say, mix atrazine and zimazine, which are structurally very similar, then the microorganisms are forced to adapt faster, maybe, and then the degradation of atrazine might increase. I have not done this kind of experiment. Maybe another small project for a student of your group.
Thank you for so many suggestions. Okay. Is there any question?
Yeah, there's more. I
Comments?
see 5. Thank you. No, that was only. Thank you.
Yeah, here, Andreas, you see here is a chat box.
Ah, there's a
Here.
chat box as well.
Yeah, Pang
Up to now,
Xiaoyang.
are there any proper suggestions on the spray methods of mixtures to eliminate environmental human rights? Pooh, that's far from my expertise. I don't know. I don't know. I must say. I can't answer these questions because I'm not working in the application field. How to do it? I mean,
so another project.
Yeah, that's also that's also in the European Union. I read that they will try to reduce the pesticide applications by 50% up to the year 2030. And so, yeah, if this happens, then of course also the environmental impact of pesticides will be reduced, but maybe also the agricultural yield on the fields, because more diseases will harm the yields. Yeah.
Maybe I ask this question from another point of view. So this spray method could be, for example, you use different formulas, different solvents.
Yeah.
And in this case, this formula is kind of compound, and they can also affect the pesticides.
Yeah, that could be. That could be. In our experiments, we did not use formulations, but we used just the active ingredients. But yeah, this is also and still another project to look at the effects of the co-solvents of the. Yeah, that's true.
Too many gaps.
Well, you are still young, Rangji. You can look at all these all these things.
Yeah, I need a young student to do this. Okay. So any question? So I see there's no question, and we are all satisfied with your talk and the answers discussion. And Now, okay. That's also the time, yeah, to closing. So thank you again, Andreas, for this very good talk, and also this inspiration to do further research.
Yes, yeah, it
with
was
our
a pleasure. I really like to see your face and to hear your voice, because it reminds me on the time that you have been with us.
Yeah, so
Long time ago.
hopefully next year, hopefully we can travel freely in the world, and we visit you, and then you can visit us in China.
Yeah, that would be nice. That would be nice.
Okay. So thank you again. Greetings on the colleagues in Aachen and your family.
Okay. So all the best to you, and good luck that Corona, all these ugly things will disappear very soon, and we are free again to travel.
Yeah. Okay. Yeah. Thank you.
Okay.
So bye bye.
Then
thank you,
goodbye.
Mr. Shepard.
Bye bye.
Bye.
Ciao. Ciao.
Bye.
Thank you, Mr. Lee.
Bye bye.